This particular example is a continuation of example number one, but in this particular example, the helical compressive springs are subject to fatigue loading. When we talk about fatigue, we are talking about cyclic loading, specifically speaking. Um, this problem, there's a preload of 50 pounds applied and it fluctuates between 110 and 150 pounds. So basically what the problem is saying, you have a spring. Initially, the spring is here. There's no loads applied in the free form. Then you go ahead and you do apply some loads to your spring. And this is your preload that you're applying a load of 50. Then beyond this is where you apply this extra load of 110, and it fluctuates between 110 and 150. This is where your fluctuation occurs, and the problem says it has a dynamic inch of 1.2. So what this is really meaning is between this point and this point, this is fluctuating between these two loads, and this dynamic is 1.2 inches, the dynamic deflection. The problem also says that the forcing frequency in the problem is 1000 RPM. That is a requirement. 10 years life and 1 operation shift. We're assuming that is pin and cold drawn. This is important for fatigue, for the properties that we're going to use. Is squared and ground ends. This is for buckling of the spring, and you start with initial spring index of 8. The fatigue analysis has a design factor 1.2. Now this is important to be careful with this, because we know that there is a requirement design factor already embedded in your analysis of 1.2 for springs, right? And then this is an additional design factor that the problem is requiring. So that means that your total design factor will be an multiplication of these two design factors. So it will be 1.2 times 1.2. The design factor we use our analysis will be 1.44. So wherever we use our design factor, that's what the problem we will use. The problem says C is equal to 8. We really do not know your diameter, so we need to start with something. Let's start with the initial guess from your static analysis. So the initial guess would be from static, okay? From problem number one. So the next thing we need to know is what type of spring it is, right? So are we designing for infinite life or finite life? Typically, this is for infinite life. Springs are designed for that. But it will give you 1000 RPM that's given in the problem. We know that 60 minutes in 1 hour. And we know that they are typically a 40-hour week. Is a working shift. And then 52 weeks. 1 year, and this gives you for a span of 10 years. This is given in the problems. This is given in the problem, so this gives you 1.2 times 10 to the 9 cycles. Know that your your required life is bigger than 10 to the 7. That means it has to be infinite life. Okay, so that means that in your problem, your equivalent fatigue stress has to be less than your endurance stress length as well. Okay, so in your the next thing that we want to do is we want to find what your Fmax are, Fmax and D, and you need to multiply that by your with your design factor. So that gives you 1.44 times 1.50, gives you 2.261 pounds. F minimum will be MD times F minimum times what's applied in the problem is 1.4, applied in the problem is 1.10, so that gives you 1.58.40 pounds. The initial preload will be ND times what is applied. So it's 144 times 50. That gives you 72 pounds. So these are the loads that we'll be using in our analysis. Okay. So we move on and we start our analysis, and we, as I told you, we're going to start with 0.2437 as the initial guess, and this is actually should be 1.90. So remember, this comes from your static analysis where this was given as A minus D, and for the property of material that we are using, to this, we found what this A and M should be. And this is a function of your diameter. So we find your ultimate tensile, ultimate shear is multiplied by this. So this is the value you get. The yield will be 0.45 of that. So that's the value that you get here. Okay. So we will move on. The next thing we want to do is we want to evaluate what your alternate and mean are. Note that your alternate, just to give you one, will be this particular value, 261, 261 minus 158.40 divided by 2. So that's how you get 28.80. This is how you get, adding these two and dividing by 2, you get 224.64. Then you check this value, you check all these values that you get from here, you check this value that you get from here. We know C is equal to 8. Your diameter, well, is given 0.67. So we know all that information. I think I got this wrong. 437. So, and we know what your KB should be for C equal to 8, 1.17. So evaluating all these values, this is how you get these values. So typically, the way I do this is like this. So in case you have to multiply by any other factor here, you can. In our case, we multiply all the factors here at the load. So that basically, that will give you the same value. So we got what your mean is, your alternate is, and then you find the maximum. So this is your maximum stress. You can see that your maximum stress does not pass the check. Okay, so that means that we go here, we can see that this doesn't apply. Let's go to the very next gauge up and let's see what happens. For that, I am going to show you what happens in the Matlab code. Let me pull the Matlab code for you. Just give me a minute. Okay, so this is a Matlab code. You can see I changed these values. This is 1.2, needs to be changed there. This is your initial load. This is 151, 110. This is your standard. This is the additional factor the problem is giving you. I like to just say this is my second try. So let's run this and see what happens. So when I run this, this looks like, it looks kind of promising. You can see that this is all looking good. I do all the analysis, and you do all your analysis, but then you run into one specific trouble. Although your stresses and all this checks and everything is positive, your factors of safety are bigger than 1, all of them actually. But when you go and look at your active number of coils, your active number of coils doesn't satisfy. Okay. Picoviolet. So since that doesn't satisfy, that means I have to go one level up. I will have to go up because the criteria is 3 and 15. So if I put this equal to 9 now, and I run your code now with 9, and I want to change this as my third try. So we are not, just to keep everything separate. So now my third try, I do all this, and now you can see that this is between 3 and 15. So this is satisfied. This is great, and my initial loading is great. But when I check my working load, the maximum load, you can see that it fails. It's less than 1. So this is not a possibility either. Since that's not a possibility, then I will do another try, and I will let you show. I'm not going to do this for every possible case here. So then the 9 is actually what works here. So this is a 3. So this is the case that I ran for. The rest of the analysis, you can see that I run your code, and your code gives you all the information that you actually need for the analysis. Okay, so that's why we went. I want to continue the analysis here now. That's where we went with the next one up. Okay, and you can see that for this particular load, these are the values that you get after you replace your diameter. And then you alternate. Obviously it's going to change, right, because the diameter changed. It's bigger. So these are my new loads I have here. Your fatigue, then I determine your fatigue, and now you can see this is less than sigma yield, so therefore we are in good shape. Then we move on, and again, just to show you, if I use 8, what happens. So you need to find first your spring mechanics, where you do your spring. This is from static again. D is equal to C times your small d wire diameter, and find your mean diameter, and find your spring rate. Then you know your delta F and delta Y. So this is 48, and the number of coils. Find NA gives you 68, and you can see that this doesn't work. That's why I told you when I ran the code, I know it's not going to work, and I just ran the code for 9 to 8 because now within the range. You always have to make those checks, and you cannot just do fatigue without checking actually static as well. So I do the whole analysis with 9 now, and you can see that D is equal to this, K is equal to this, and I get what your initial load would be with F minimum. So that's given here. The working load is there. Your clash is there, and your total deflection is 4.68. And then now I go and find the number of coils. You can see get this value. The next quarter up will be 1175. This is within the range. So this is again. So this is 11 here. So this is within the range, and this is 13.75. So then you go and you do all your static checks now. Okay, so you do first for preload, because if it fails for preload, we are really wasting our time. But the code does this for you as well. You can see that this is obviously way below our sigma yield. And okay, so for the preload, we are good. We move on to the working load. That's a maximum load in static. And you can show that this is also bigger than 1. So this is also acceptable. So we move on, and a safety as shut is when your is completely compressed. So as shut, this is how much you have as shut. Your K times this is your the load that's applied to the problem. Then you move on, you calculate this, you find 74, and you can see that you can show this is good. Okay. Then we move on, and we have to check the stability and multiply by your diameter. This gives you 13, and you can see that your maximum L sub 0 is less than L critical, so we are good there. Your working conditions also are below this, so your stability is good. Stability, buckling will not be an issue for this spring. Next thing you have to do is you find your torsional strength at 10 to the 3. This is given by this equation right here. Gives you 106.77. And then from this table, this is the cases that we are working with for your particular problem. So it's 0.49, 47, 46. You multiply, this is 10 to the 7, 10 to the 6, and 10 to the 5. This will help to plot our SN diagram. Let's find how much is your infinite value, your endurance limit, sorry, and the factor is equal to K equal to 1. Remember, if I had something with a room temperature, right, if a temperature was given, then this value could change, just like we did in the past, in our previous, when we did staff analysis. And this is for 50% reliability, but this was a different number. This no longer will be 1. And if there is corrosion, then you have to have a corrosion factor in there as well. But in this case, it's saying to assume there's a room temperature, 50% reliability, no corrosion, so all this is actually equal to 1. Using method number 1, this is the method I like because it's more conservative. And this is the data we get from Similarly, and multiplied by K infinite, which is actually equal to 1. So this is equal to this. And then you just use this equation right here, right? And this is what you actually calculated in your problem at ultimate shear. Okay, you calculated that. Okay, so we already calculated that in the previous slides. So as we move on, there's a method number 2. This is what your book recommends. And I'm not a big fan of it because it gives you non-conservative analysis. And you can see if I'm using Goodman theory, gives me 168. And if I use, actually we like to use more Gerber than Goodman. If we did that, then you can see it gives you 98. But still, this is way below. And I like this, this method is way more conservative for springs, and it's the method that we typically like to use. But depends on the application, maybe you could use one or the other. So now we plot everything, we put it together. You can see this is at 10 to the 0, this is 10 to the 3, 5, and this is 7, and then obviously there is a, these are all the plots that we have. So there's somewhere here, this is 10 to the 6, that's why we got this value there. And this is what your plot looks like. And your value, we want infinite life here, right? So we want everything here. This was equal to 40, we got it from here, 47.08. Okay, so your sigma equivalent has to be less than this because this is what we want to design for. Remember, we got this from the beginning of the problem. So we know that this is actually indeed a infinite life problem. It's bigger than 10 to the 7. So we have to, in that case, design for infinite life. So we move on with the analysis, and then remember, this is equal to 1.15. This is for C equal to 9. And then we replace all these values there. You can find what your maximum is, your minimum is, and these are the values. And then you determine your slope R that you need, is 0.25. The Goodman stress, then you need to find these values, find your initial load, and plug in the values in this equation. And that gives you 14.62. And you can immediately see this value is way below this value, so we are actually in good shape of designing for infinite life. So this is check, this passes. You also want to check factor safety for fatigue, and that's done by using tau A, and it gets 1.54, which is also a check, and we are in a good shape there. The next thing that we want to do is check your frequency requirement. You don't want the spring to wobble to enter the resonance. So for the values that we have in our problem, and I can write them down here, replace this value, get this, and your forcing frequency was 1000. So when you divide this, you get 2.14, and this is less than 15. So it says it's not going to, the coils are not going to hit each other, and resonance is not going to be an issue. So all the passes check. The gauge that we used was gauge number 1. And then you just put all the values here, your outer diameter, your inner diameter, your hole, and round it up to the next, this is 2/1/8. This has to be smaller. This goes to the upper end. This goes to the lower end. this is the pitch and this is your angle. This is what you will give the designer as your final answer, saying this spring satisfies not only fatigue, but it satisfies also static. Okay, so it satisfies both. So this concludes this particular example on fatigue of helical springs.